All right, let's go ahead and continue. We just finished up talking about the fork process in the last video, so we're going to continue on talking about what is a little more of what the operating system does. Now you hopefully have a good idea of, from an application standpoint, what's going on, because when you want to create another process, the fork is the command that is used. All right, we talked about the queue, different queues lastly, and specifically we just did an example of forking a child. We should have really had two arrows coming out and then going up top. All right, schedulers. The book delineates different types of long-term and short-term schedulers. Yes, these are talked about. They're not necessarily spelled out in an operating system when I've worked on OSs, but it's good to keep in mind because there's different goals. What's really important here is that your scheduler is always going to have a different goal, and you always have a scheduler for a specific goal. So here, the long term is which one should be brought into the ready queue, aka if they're on the disk and they need to be written out to memory. That's probably for a long queue. That's a different strategy. You want to always make sure the disk is in usage because the disk is slow. So the idea is you want as fast as you can bring them in without interrupting the current executing processes. And then the short term is, all right, you have the process in memory. How do we determine which one should execute next? So a little different goals. Short term, you want to have quick response. Long term, you want to get it out as quickly as possible without interrupting anyone or minimizing the interruptions. All right, another example here. In the ready queue, maybe you'll swap in partially swapped out process, swap it out back to the UI queue. One thing we haven't talked about is if you're running out of main memory, what does the operating system do?
Breaks that memory.
If you're running out of main memory and it needs to bring in a process that's not in main memory, what's going to happen?
The process and be stored to the disk.
Disk, and then the new one. Right. So if it's put to the disk, it's put into which scheduler?
The long term.
The long term. There we go. That's why you have these. It may be different reasons, not just the new creation of the process, but you might have run out of memory and now you need to start swapping processes in and out. And that's essentially what we're trying to talk about here. Oh, this is the medium-term scheduler. When you swap out a process, operating system does it in chunks. You may not have to swap out the entire process. Maybe you only swap out part of it. And the operating system might be really smart and figured out you haven't used this piece of memory in a long time. We're just going to write that to disk so we can clear out memory for something else, and we'll just execute your process. And as long as you don't reference that, we're good to go. If you do, then we'll have to bring it back into main memory.
That means we have to keep track of how long you've used that section or how long before it can access that section.
Yep. What does that sound like?
Bookkeeping.
Bookkeeping. What other structure and architecture do we use that does something similar? Can't remember the term?
Are we talking, we're talking about, you said structure.
Mm-hmm.
I remember the flag.
I'm thinking of an algorithm, swapping out algorithm.
Oh, well, what algorithm are you thinking of?
I can't. It's when you do the full movement. Okay, I've used this much. Oh.
What was architecture all about?
Cache.
So
I was thinking of the mechanism by which it tracked it.
Yeah, least recently used. That's the theoretical best one, although that's really hard to compute, so it's usually some heuristic based on it. It's the same thing. Essentially what has happened is we've turned main memory into a cache of the disk. So when I ask what other type of caches exist, main memory from disk, that's essentially another one. Your processes are being cached in main memory when a large amount could be on disk. It's similar concept. Similar, not the same, but similar. All right, short term's done very frequently, aka in milliseconds. Yeah, your processes are usually switched in and out, I think about 10 milliseconds, if I recall, is what the Linux scheduler did for a while. It might be 20. Long term is done very infrequently. Your process maybe is waiting on I/O forever, so it might go to the disk. Long-term scheduler controls a degree of multi-programming, basically how many programs are in main memory and how many are on disk. All right. Last one is probably really important. There's actually a third category. You have IO-bound process, spends all its time waiting on IO to complete. You have CPU-bound process, which spends all its time on computations, scientific stuff, for example. You also have a third one that's not really mentioned here. It's called memory-bound, which means it's constantly waiting for memory to come back. And that can be, when could that be important? Ooh, that's a tough one. Let's go back to IO. Why is signifying when something's IO bound important? What's the behavior of that program?
You don't need the CPU to be locked up for the entire execution.
Right, so you know if it's IO bound, it's going to do a short burst on the CPU and then go into IO waiting, the waiting state. If it's CPU bound, what does that mean?
It's going to hog up your CPU resources.
Right, it's going to use the CPU a lot. It's not going to really do much IO, so it's just churning on that CPU. So memory bound means what? It's
Isn't that like an IO bound process though?
similar,
Is it memory?
but it's
Well,
waiting
going
on
to disk, you know.
It's not going to disk. It's
Oh.
waiting for main memory.
Oh,
It's kind of a hard one.
so the ones you're trying to just slowly schedule into your ready queue?
Yeah, it's technically ready, but it's memory bound. If you're on a, remember the memory is a shared resource, so if you're on a multi-core system, how many memory bound processes do you want to be running at most? If you want. But how many CPU bound processes can you run? As many as you want. So if you wrote a smart scheduler, you could say, hey look, this memory bound process, let's only run one memory bound process at a time if we can, and then the rest can be CPU bound or even IO bound. So hopefully you can see the scheduler can actually take in a lot of different attributes at once, because if you have two memory bound processes running at the same time, they're just going to slow each other down.
Well, why would you have a memory bound process to begin with? Just because of
Sometimes it's memory bound, that's all you can do. If you're doing some really complex simulations, it might be jumping out of memory all the time.
Gotcha.
Or if you just got to store a large piece of data to memory.
Yeah, and you just got to go through the memory, you know, you're memory bound. You're just using the system. It's not, you have some things they just have to use a lot of memory. There's no way around it. Okay, context switch. This is when you jump from one process to another. So it's switching between, one process and another. It's represented by the process control box or board. Context switch time is overhead. The system does no useful work while switching. When you change from one process to another, the CPU has accomplished essentially nothing except for being able to now run a different program. It hasn't done any actual work. So you want, the length of the switch time is dependent on your hardware support. Schedulers must consider the cost when actually scheduling. You want to minimize switching as much as possible, and you want to make switching as cheap as possible.
So when when you had that slide up and had the process one and we were switching, we had the idle time.
Mhm.
That wasn't context switching. That was
No, that's context
that's
switching.
context switching.
Here's the
There's
picture.
Another switching later.
So
That's it.
going from this process here
Mhm.
down to this process executing, all that is a context switch. And from this picture, it shows that your CPU is flat out idle. It is not doing, well, they call it idle. It's doing work, but it's not doing any useful work. All right, schedulers, context switch.
It's just sending all your data off to the government.
It's like city. Yeah, but usually once you do that, you go and do something else, right? Right. Well, that's happening. You're able to do something. It's yeah. You're not going to
It
get
all
off
runs in the
One
background,
test.
right? Yes.
Huh?
The walk from one task to the other.
Right. It's you know, that task is now IO bound, right? It's government bound. Stamp it and then you go do something else. All right. So we talked about fork. Let's go. Let me make sure I said everything or told you everything you need to know. Parent creates the children, which in turn can create other children, forming a tree. Let's see. Generally, the process ID is managed via the PID. That's your process identifier. Hopefully I said that. Ways of sharing resources. Parent and children share all resources. Well, kind of, before they're forked. Children can share a subset, or parents share, children share no. Okay, that's what it's saying, ways it can't. You can't set it up to where all resources are shared, or none of the resources are shared, or only part of the resources are shared. All right, parent and children execute concurrently, or at least seemingly concurrently. If you have multiple CPUs, they can execute concurrently. And a parent waits until its children are terminated. Notice in our program that was not necessarily the case, but in good programming practice, you better be doing it that way. Otherwise, sadness will occur. Yeah, so you want the parent to terminate after all children terminate. That's what you want. Otherwise, the parent can just terminate at will, or determine when the children parent terminate, because the parent can actually kill. Oh, it sounds so bad. Kill its children.
You've been too long in the bathroom, you're dead.
Yes.
After bed resources.
So going back to the resource sharing, so like how we did my age, if we stored that as a pointer instead, would that be?
No, because you're just sharing the pointer.
Right, that's what I'm saying. So if we had done the same thing,
Oh, but created a pointer?
but made it a pointer instead, would the parent have said I'm 14 as well?
No. No.
Why?
Because when you make a copy of a process, it copies over the heap as well. So what Chris is saying, let's go ahead and do it, in case I'm terribly, terribly wrong. So int my age equals new int, and then store my age equals 35. Down here we'll go and put my age 14, and then over here we'll print off my age of the child and then my age of the parent. All right.
Do you have to have a semicolon after my age equals 35?
I sure do. Good catch. Whoa, you beat Chris to the punch. Nice.
I wait for you to do it.
Nice. Nice. All right. Anything else, guys? All right, let's go ahead and run this. See if I'm. Oh, new undeclared. Oh, that's because that is C++. I'm too used to data structures, so we'll do malloc size of int.
Oh, what are we supposed to be using?
I'm using C.
Oh, okay.
You can use either. If you're a real programmer, use C. Boom. All right, let's see what he did. Nope. My age is still 35. Because it copied the heap. Remember, it's copying everything, including its heap. It's creating a new heap for the child.
But with the same pointer.
But with the same pointer. Ah, I see what you're trying to say. Remember in architecture, the pointer inside of a process is actually a virtual pointer, not its actual physical pointer. So it's copying its virtual piece of memory over as well. Good catch. Good catch.
So then how would you get them to share?
You have to use something called memory map or shared memory function to get that to happen. And we will get to that in a bit today. In fact, although we might be running out of time. All right, process creation. Any other questions about this one or the piece of code?
Maybe.
Maybe?
You should give me like 20 seconds. Because like I tried to compile it and it didn't work, so I installed some other stuff and then it was like changed the LD to a D. And I did that and then it worked, but now the other way is working, but I want to change it back to it.
One day I'm just going to record what you say, and I don't know what I'm going to do with it. I'll do something cool.
Pull up though. It's important.
All right, child's duplicate of a parent has a program loaded into it. Fork system call creates a new process. Exec system call used after fork to replace a process's memory with a new program. All right, this is something different. Exec is if you want the child to run a completely different process, replacing its current one. Meaning that once you run exec, any code after exec does not happen because the current process has been replaced by a different one.
Wait, so that file was C that you compiled?
Yeah, it's C.
It was the whole time?
Yeah.
Okay, that's probably why, because I made a C++.
I know. Too much data structures. We need to go back to doing data structures in C. Yeah, that'd be good. Oh, that would be great. Oh, that would make me so happy. It would make, like I said, it would make me so
Why
happy.
do you like C so much?
Because it stops people. It does two things. One, actually, it really just does one thing.
Makes you happy.
No, really just one thing. You can't be a successful terrible C programmer, or it's very hard to be. A successful,
Teach a man to fish.
terrible, what?
Teach a man to fish or give a man to fish?
Right. So,
Not help you at all.
what?
It does not help you.
Right. If you're a terrible C programmer, your program's not going to work, and you're probably not going to get hired, and you won't be doing it for very long. If you're a good C program, you'll be able to keep doing it. Why do I like that? Because in the workforce, I've seen Java abused way too much. I hate seeing the code. I really don't like seeing the code that's been produced by Java. Same thing goes for C++. Actually, C++ is 10 million times worse because people will go crazy thinking that they need to integrate every single possible feature of that language into their program. And then JavaScript, well, JavaScript has some cool things. Hopefully they'll be able to iron out.
So why don't we teach C then?
We do essentially, but C++, they just chose C++. Look, I'm happy with C++ because usually the other common choice is Python, and
I've heard
that
that.
one just gives. Python's a great language. I have actually no problems with Python, but starting people in Python I think is a poor decision because Python does too much for you and you don't understand what's going on. Great sidetrack. Any others?
It didn't compile with the LD for me either with the C, which makes no sense.
Okay, well, I'll hopefully be able to help you during lab time. All right, when Unix calls fork, it allocates a slot in the process table. Failure state, if no slots are available, that's probably never going to happen anymore. Well, it can, but good luck. Well, you just do a fork bomb, but besides that, it's not going to happen. Gives it a PID, makes a copy, moves the child to ready, returns PID of child to the parent and 0 to the child. Note the above character. Well, we did this already, so hopefully this is clear. Return less than 0 on a failure, 0 the child, greater than 0 parent. So when I ask you to check for the success, which I did not do, you need to check if the return value is less than 0.
You only checked if it returned 0.
I just ignored it. I just said, if I'm 0, good. If not, oh well. I didn't.
Oh, okay. Well, the actual.
What I was supposed to do is if
Okay.
return PID is less than 0, you basically say, sure, we'll put it in here now. Printf unable to create process exiting. And this is great because I get to also show you that there's the exit function, which basically says ignore any other code, just terminate this process now. And you pass in what value you want to return. 0 means that it was successful. Anything besides 0 is a failure. And there's actually a long list of different failures, but I'm just going to give it a 1 saying this process failed. Naturally, I doubt that's ever going to happen, but now you see how you check.
But then the next check you've got is if it equals 0,
Then
you
you're
say
the child.
You're the child.
Otherwise, if it's not 0, I am the parent.
Because if it's not 0, but it was less than 0, then we exit.
Yeah, because if you're less than 0, then something bad happened. Remember, there are different processes when you check the return value of fork. There's 2 processes happening now. Hey, here's a good picture. You fork, the parent probably does some stuff, goes to waiting, child does some execution, then when it exits, it's done, and it signals the parent, hey, I'm done, and then the parent can resume. Generally accepted flow for forking. Oh, here's an example. Fork, getting the PID. Wow, this code's a little hard to read. Printf, fork failed, exit. Okay, they did -1. Woo. If PID 0 on the child process, so that's this exe, clp, ls, null. Replace the child process with ls, which would list everything. And then the parent, wait for it to complete. Oops. Wait for it to complete, then print off child complete. And usually, when you're done, you want to call exit 0, saying you succeeded.
Wouldn't that be a horrible way to do that, though?
Well, I will say the formatting of this slide is pretty horrible.
Well, I mean, so if you're just going to do an LS anyways, you could have just done that parent.
Okay, if you were
See, you're going
sure.
to copy the entire program and then just say ignore that. Isn't that a costly operation?
Yes, but what else are you going to do?
Just create a blank process?
There might be a command to create a blank process somewhere. I have not seen it yet, but I'm sure it exists. That's a good point. All right, a tree. So, top one scheduler, PID 0. Who do you think holds PID 0?
Well, you.
BIOS.
No. BIOS is done when the operating system starts. What part of the operating system?
Kernel.
The kernel. Kernel 0. All right, page out, FS flush. These are for hardware or other device driver type things. Init is usually PID 1, and that is going to actually start creating the processes you want. Notice you might have a login, X session, your GUI, maybe a shell. Here's CSH, your actual shell, and then you can run LS as well as cat. And then those can all be created and die as necessary or destroyed. Then over here you might have another person trying to run Emacs. Or, wow, Netscape, really? Whew. Picture makes sense? Good. All right, fork, print off L0, fork, 2 people are going to print off L1, fork, 4 people are going to say bye.
What was the first thing I
Everyone good with this one? You get it all right. We'll add another layer to it. Now we have 8.
V fork.
What?
V fork.
V fork. Ah, yes, that's right, V fork. And then I'll fork the new process with this. But yeah, that sounds good. Any questions? Beautiful. Basically, once you fork, it says something and then leaves.
Wait, what was the difference down between that and then the first one?
First one just forks 3 times, period, no ifs. Over here, it'll fork, and as long as I'm not the child, I'll fork again. As long as I'm not the child, I'll fork one last time.
Okay.
So then the children never fork, is the point of this. All right, exits, gets out of the process, waits for something to end. You can the parent, I keep forgetting how terrible this terminology is. The parent can always abort the child. And there's something called cascading termination. Do not allow children to continue if the parent terminates, so all children terminate, aka if the parent terminates. Some OSs do that, some do not. Obviously mine did not. If the parent dies, the child can still keep going. All right, usually a process can be independent or cooperating. If it's independent, it's not going to do anything with the parent. So far, everything we've done has been independent, but you can have cooperating processes that try and work with one another. Might be able to okay, hopefully the reasons are obvious. Really, computation speed up, being able to execute more than one thing at a time, but actually modularity is also very important in convenience. For example, the Apache web server will under load start creating more processes when you're having a lot of connections. And the reason for this, there's multiple reasons. It's that take advantage of the operating system scheduling, but also if all of a sudden someone causes the web server to hang up, you can just kill the process and then create a new one when a new connection comes in. Cooperating processes need inter-process communication. So inter-process is how 2 processes communicate from one to another. There's 2 models. One is shared memory and the other is message passing. So shared memory is where they're going to say, I'm going to share this piece of memory with you. Let's go ahead and anytime I write to the memory, you will get that read. So they're literally sharing a piece of memory. The other one's message passing. You say hello and then they can receive it and acknowledge or whatnot. Yeah, so under, this one looks like shared. Yeah, shared are independent, and then all of a sudden they have a piece of memory that they wish to share, that they can both access. One thing to keep in mind, in general, shared memory is set up before you fork.
Is the message passing?
What's that?
I think the one on the left is the message passing. Process A sends a message to the kernel, the kernel sends that message to process B.
Yes, on the left is message. Yeah, that makes sense. Left is message passing. The other one is shared because you're going to send. Yeah, good call. Good catch. All right, let's go code this. Let's go ahead and copy fork over so I don't have to do it. We'll do it to shared fork.c. Go back to shared fork. I have a bunch of information here. That's great. So there are different ways to share memory. If you read the book, it's going to call out something called chmem for share mem. I think a far easier way to do this is to use a function called mmap. Map or unmap files or devices into memory. Creates a new mapping virtual address space of the calling process. So you just call mmap, a pointer to the memory, how long it is, and then a bunch of flags if you want it. Hopefully they give you a good example, otherwise we're going to be sad. Oh, this is a long one. There we go. That's not what I wanted to see. So I'm going to use my notes from the do not commit. There we go, lab 1. And I think I was using the producer consumer. Yeah, let's see. There we go. All right, now that I've gotten that. What's going on in mmap? The first one was null. I remember that not being anything of importance right now. Creates a new mapping in virtual of the calling process.
The kernel chooses the address.
Then the kernel chooses the address at which to create the mapping. This is the most portable method of creating a new mapping. If it's null, then the kernel takes it as a hint about where to place the mapping. The mapping will be created as a nearby page boundary. So it's actually going to, this should map or unmap files. It should create something for you. Yeah, it creates it. All right. So I call it size of item. I'm going to go up here and we're going to, I don't know, int star randoms. Basically random numbers. We'll do size of int times 10. We'll tell it to be 10 random numbers. We want to be able to always read it, always write to it, anonymous, so that it doesn't matter. Anyone can have access to it, and then shared. We actually want to share it, and I forget what the last two mean, but not important.
So what's randoms we're doing?
So randoms is just a variable I created. We're going to have this.
That's a pointer.
Yeah. Actually, let's not call it random. Let's change this to PIDs. There we go. Store process PIDs. That way it actually is something somewhat useful. And yeah, they totally need to be longs now. Oh, they do. Actually, if you want to be perfectly correct, it's PID_T, which I bet you on this system is a long. We'll go ahead and do it this way. All right. So now, create a child process and get my PID. If I'm a child, we're going to get rid of this whole image thing because we don't need to be playing with it anymore. Perfect. All right, so if I'm the children or the child, I'll go ahead and put PID sub 1 equals, what was it, my PID. And then down here, PID sub 0 is my PID. And then after the wait, I'm just going to create a little for loop. Right now we only have 2, so that's fine. We'll just do %LD, comma, and we'll do PID sub I. \n. And now we'll go PIDs. There we go. All right, so let's go over here, GCC, shared fork -o, shared fork, and let's go ahead and run that real quick. Ooh, I did not like that because I did not include probably sysman. All right. Yeah. All right. PIDs. So I'm 1894. The next one's 1895. Run it again. 1901, 1902. All right. Not too useful right now, but hopefully you can see that by writing to it, you actually have set up a shared memory, so it was actually able to store that. Let's go. I created 10 of them. So if I'm one thing, let's see what would be good here. Would be a good way to do this. So I'm forking here, get the PID. If it's less than 0, something bad happened. If it's the child, execute this. If I'm the parent, we'll go ahead. What do I want to do here? We'll go while. Actually, no, let's stop here. Let's do this one thing at a time. If my return PID is greater than 0, aka I'm the parent, we'll go ahead and fork again. And then we want to actually have the return PID equals the fork. I don't know why I put, oh, I know why, because I put a space. And then we'll again update my PID afterwards. So in other words, it's going to fork. I'm ignoring the check for now, but it's going to fork again afterwards if I'm the parent. So this should create 3 processes, right? All right, but then this is a fun memory change because PIDs 1910 are, we kind of switched up what was where actually why did it happen this way? Might be a bit.
Because you set a hard-coded 1 into the children's.
Right. You look at the parents, yeah, 1910 overwrote the old one. All right. So we need to come up with another way to think of the ID. So
Initialize them to 0, and if
right.
go
So
through it, and if it's 0, don't change that one, change the next one.
my index is 0. That's the parent. So let's see how to do this. So right here we'll go if return PID equals 0. And then we want to, we'll do, what is it? My index plus plus, else, ooh.
What are you doing here with my index plus plus? Or you're in the...
That's his index that he's currently
okay,
residing.
gotcha.
Then we'll increment it there, and then of course we'll increment it down here. And now we can just do my index. And over here we can do my index as well. And I'm just going to go down here and hard code it as 3 for now, and we'll get to that in a moment. So now, okay. Huh. Came out a little differently. Yes, that makes sense actually.
22.
Theoretically,
we split again, so one of those I am the child is really I am the grandchild, really.
no, because the parent created all these children.
Oh, okay. Where were you? Where did
So this is if I'm a child. No, that's child. And that's if I'm a parent.
Great. Okay, gotcha. Where is he for? So if you're the child, you're just going to up your index. And what's
How's
your
that?
index? That'll tell you what child number you are?
So this was done a little backwards, I've just realized. Sorry about that. What I really meant to do, so my apologies, is that if the return PID equals, because this will make more intuitive sense. here, then I want to increment my index. All right, now this is going to make more sense. There we go, because now they're in ascending order. I wrote it backwards. Sorry, guys. So let's go from the top just to read this, because it is confusing. PIDs is copied, shared memory. Currently, I have it as 10 PIDs. My index is 0. So when this fork happens right here, we're going to have two processes. Currently, its index is 0 for both of them, but the return PID will be different. We get the current PID. Less than 0, something bad happened, let's get out. If it's greater than 0, that means I'm the parent. Let's fork again, and then I'm going to get the PID, and if from this fork, from the parent, if I'm the child of the second fork, I'm going to increment once. So then you have two children, one's has a my index of 1, the other has an index of 0, and then notice under here I increment again, so the two children will then become
With that,
1 and 2.
that second child, shouldn't its index be 0, not 1?
It would be 0 at this point, but then when it comes here, it increments to 1.
Both children are at 1?
No, now one children's at 0, the other's at 1.
Right.
And then when you come down here, the one at 0 goes to 1, and the one at 1 goes to 2.
Oh, okay.
So if I'm the parent and I do return PID, that's the parent ID of the parent?
If I'm the parent and I get the parent PID, get parent PID.
Return PID equals fork. What do you okay,
Whenever I call a fork, that's the return PID. I'm just trying to say that the return PID from fork, because the return PID from fork is going to tell you if you're a child or not. Because if fork comes back as 0, then I'm a child. All right. Hopefully you can see the point of this is that if I'm in here and I want to do a bunch of them, less than 9, we'll do 10 for now. I can put this in a quick little loop. And then hopefully, if I did this right, the parent is going to create each of these children and then move on. Let's not make it 10 for now. Let's go ahead, because that might be a little confusing. We'll go ahead and make it 4. Oh, that was beautiful.
Wait, so if I'm the
this is
child,
beautiful.
my parent is named, or I'm the child, my parent is.
Oh, this is great output. This is beautiful output.
So the first one is.
Actually, children are done. Wow, something weird happened there, but this is beautiful. So I'm the child, and my parent is 1934. 37, I'm also the child, my parent's 1934. 34 says, oh wait, I'm the parent, 1442. Oh, 36, I'm the child, and then it exited right here, and we moved on. That one did not wait for all the children to complete, which is not good. Wait for all children to complete.
You had it in between, though. You had it in the middle of the.
Now I should have waited for all the children to complete. Spin execution of the calling until 1. Okay, how do you wait till all?
Oh, those are the values there.
Oh, here we go. Meaning that wait for children whose wait for any child process, wait for any child who's go to that, wait for. Okay. So, ooh, this is different than what I'm used to. Is there an all? Wait for any child IDs ignored. We may have to put this in a loop. Ooh, this could be bad. All right. Ooh.
So we got wait null. What does wait null mean?
You aren't waiting for any status. So remember that is the status you're waiting for. PID is the PID that you're specifically waiting for it to finish. So let's go back. There's different ways to go about this. We're going to go ahead and memory map. Let's see, we have 10 of them. So we'll do for int I equals 0. As you can see, this gets pretty complicated. I plus plus PID sub I equals 0. So now if we want to wait for each process to complete, if I'm reading this correctly, what we want to call wait until each process is done. Ooh, that could be tricky.
If you're just waiting for.
Yeah, this is actually a lot trickier than I thought. I thought wait actually waited for everything, but it does not, because it waits for anything to complete. And it wait for children that have terminated. Current value.
What language? This is Linux.
Oh yeah, this is Linux. Nope, that's not what we want. Okay. All right. I will have to get back to you on that. We're going to do a cheap way of doing this and just have it sleep. I'll have to get back to you on this. There's different ways. I have different solutions for this. I want to make sure I present to you a clean one that is easy to understand. But we clear this all out. Go back here, and now we can run it. It's just going to wait for a while. All right. Now we have different processes. We're going to go num children equals. We'll start at 4. That way when over here we can multiply it by 4, set them all to 4. And now what I'm going to do is basically delete this. We're going to create the child here. Whew. For if I is less than 4, and return PID does not equal 0. So while we're still going through, and I'm not the child, go ahead and fork, and then if I'm, oops, now I can combine this by just saying, always get my PID, and then if I'm the child, update my index.
So the child process is going to automatically, as it's doing, get the its PID.
That should actually do it correctly. Or maybe not at all. Let me see, return. So the first time it actually does something. There we go. Now it's going to create, they create 4 children? I've created 5. No, it created 4. Perfect. And if I go over here, I can change this to 7. See, 1, 2, oops, it did not do it. Because this for loop, num children. There, now we should have 7. 1, 2, 3, 4, 5, 6, 7. Perfect. And then we just need to fix this PIDs at the end. I wonder why one of them didn't get set up correctly. We'll have to check that in a moment. Num children. Do I have something hard coded here? My index. Ooh. I'm child, whatever my parent is. We'll go ahead and tell it. My index.
As long as the parent, what's that, number children and return PID is not equal to 0. Increment.
Create the process. If I'm the child, increment it.
Each of those children are incrementing their index, though, each time a new child is created, because it's not entering that for loop.
Yes, you are correct.
So you just need to take that and part and just put that around the return PID, MIP, PID.
Wait, say again, sorry?
So
Yeah, I see what the problem
right
is.
after the first for loop, take out the and, create a new if inside of it. With
Ah,
that,
and
and
if,
just do the first two.
so, num children, right, and then if, oh, okay, I see. If my return PID is equal to 0 because I am the parent, whoops, then do these two things.
Isn't that not even?
Yeah, not equal, correct. Otherwise, if I'm the child, just make sure you're always incrementing. Great. There's probably a little faster way to do it, but that's okay. Beautiful. Well, almost had it. Looks like we got an off by 1 error somewhere. Oh, we don't need this anymore. I like how it does it out of order sometimes. That's fine. Well, it's just reversed, which is okay. All right.
I think you're still off by 1 on the front though. There's 7 children, so you should have 8 kids.
1, 2, 3. Oh. Better? Okay, good. All right, I'm going to have to come back and tell you a better way to do weight, because I should have worked differently. But hopefully you can see that shared memory starts to get a little complicated. Although really the shared memory part is actually fairly straightforward. Let me make this num children so we don't actually have memory problems. There we go.
Now, I mean, since you're already storing the PIDs, could you just throw the PIDs and the weight on?
Yeah, the problem is I have to make sure the PIDs are in that directory. So one way I could do it is just, I could have a for loop, basically wait, and then for int I equals 0, I is less than num children, I plus plus, and then you want to have a flag bool. I'm just going to call it int children. Oops. Children complete equals true. If PIDs sub I equals 0, then children complete is 0 because the children are not complete. I'm going to put it right here. So while not children complete, go ahead and execute all of this. Get rid of that sleep real quick. Children complete. Wait for a child to complete. Go look at all the PIDs. Make sure something's been written to them. If one has not been written to, then we are not complete. Keep going. This still has a race condition in it, although it may work. It worked. There's a race condition in here. And why did it not print everything? Oh no, it did.
Well,
Oh no, it didn't.
once you set it to not complete once, it never gets reset. I think the end should be in the while statement.
Right, and also I'm not checking the correct things.
Reset it to 1 right after a while.
Yeah. Yeah, there's still a race condition here. Not quite.
Did you say still a race condition?
Yeah, there's a race condition in here.
The parent
Oh
said-
wow, it says if this guy's 0, it still worked. Am I not checking this correctly? If children complete, actually that should be a 0, and then children complete here should be a 1. I did that backwards.
You should need the 0 inside too. First time after a while.
Yeah, there we go. Oh, we're still missing some. I love how it's different ones each time. That's beautiful.
Try taking out the not children complete, just do while children complete equals 0.
All right.
Just to be explicit.
But then children complete equals 0 should be 1. I had it right. All children are done. Oh no, that's working. That's beautiful though. Let's see if we can get. Hold on, can I do it again? Oh, it's not gonna do it.
You're setting them all to.
No. What I wanted to show is this right here because this is great. Sometimes flushing to output does not happen in the right order. That's what I'm trying to show you. The children may tell you to print this, but it doesn't get printed until someone else prints first. Very important to keep in mind when reading logs. Just because it's printed in an order doesn't mean it actually happened in that order. The logs are not sequential. They are always printed out of order of what actually happened. Well, you have to assume that they are probably printed out of order. They could be in order, but there's no guarantee. But anyways, here's another good example. This child got printed afterwards, and then we got it out. Yeah, so this is the long way to do it. There's probably a faster way out there. I just haven't seen it. All right, we are running out of time, and I want to make sure we have some lab time. But any questions on this one? By the way, are you able to read this? I keep forgetting in here, usually it's hard to read with a black background.
That purple is a little hard, but I'm up front here. I can see it.
Okay, good.
I don't know if my back. How is back there?
I can see it.
Okay. We still have we have to talk more producer-consumer. This is actually a producer-consumer model because the children are producing their PIDs and then the parent process is consuming them by printing them out. So this is a simple producer-consumer model. Let me go and stop